APLA organiza la primera reunión virtual latinoamericana de petroquímica, que tendrá como objetivo generar un espacio de nuevas experiencias y oportunidades, desafiando las nuevas tecnologías y adaptándonos a los nuevos paradigmas de negocios. Sigamos conectados. APLA Anual Virtual, 9 y 10 de noviembre. Los esperamos. Hola, muy buenos días y bienvenidos a una nueva sesión con expertos de APLA. Hoy estaremos presentando K-COT, una tecnología catalizadora de olefinas de KBR. Estaremos junto a Paul Van Helmond, que es director de Olefins Technology de la empresa. Esta presentación será en inglés, así que Paul, bienvenido, welcome.
So today I will be talking about K-COT, Catalytic Olefins technology. This is a technology that helps both refiners and olefins producers, and it should be used for people working in those industries. KBR offers a wide portfolio refining, olefins, chemicals, inorganic chemicals, and syngas. As I said, the presentation today will be K-COT, which is in the olefins family. I will quickly introduce the technologies shown here in red because they are associated or similar. FCC is our refining technology. KBR was one of the original developers of this technology. We've been in it for a very long time. Part of this technology is applied in K-COT. SCORE is our conventional thermal cracking technology, turning ethanes and propanes and naphthas into ethylene and propylene. K-COT is the topic of this discussion, and K-Pro is the newer, younger cousin of K-COT, using again a similar reactor setup, but different catalyst. This is a propane dehydrogenation technology producing propylene from propane feedstock. Let's talk about some very broad, general, overarching industry trends. In the refining industry, in particular in Europe and North America, the demand for gasoline is decreasing. And this is associated with the growth of electric vehicles. We expect that this trend will also broaden to other areas of the world, including South America. In the petrochemical industry, we've seen a continued growth, and this also applies to olefins, ethylene, and propylene, which are the largest petrochemicals produced in the world. And we've seen for many decades now that this market increases at a rate larger than the GDP. So it's therefore no surprise that people are looking at how they can produce more chemicals from the same barrel of crude. And K-COT is one possible scheme. It fits into the overarching demand to produce more chemicals from crude oil. K-COT is an acronym for KBR, Catalytic Olefins Technology. Propylene, ethylene, and aromatics are produced from, in this case, shown pentane and pentene, but it could be other feedstocks also. I'll get to that in follow-up slides. We apply a proprietary catalyst, which is a ZSM 5 catalyst that we specifically developed for this application. We use a KBR orthoflow reactor. This is a reactor that we have been working with for more than 50 years in FCC technology. Consists of a reactor, a disengager, and a regenerator, which are stacked / closely coupled. Let's look at our history in FCC. We've been at this for a very long time, started in the 1940s, and made many process and mechanical changes in FCC, and also developed continuously newer and better catalysts. In 2006, we did the first commercial application of K-COT. So this technology has been around for nearly 15 years. K-COT is an extremely flexible technology. It converts low-value hydrocarbon streams directly into high-value petrochemicals, in particular propylene. The technology has the ability to process essentially any C4 through C10 hydrocarbon, being it olefinic, paraffinic, or mixed stream. Let me list a few examples of feedstocks that we have applied in K-COT. Mixed C4s from refineries and conventional steam crackers. These mixed C4s are usually both paraffinic and olefinic, cannot be fed to a conventional cracker, but excellent feedstocks for a K-COT unit. Similarly, in the C5s, amylines, tame raffinate, and mixed C5s can be fed directly without hydrogenation to a K-COT unit. We've also got cracked naphthas from FCC, steam crackers, cokers, and vis breakers. Oxygenates also can be fed to a K-COT unit. And there is no need for feed pretreatment. For example, coker naphtha will typically contain some conjugated diolefins, which need to be processed in a refinery scheme, but these diolefins can be taken straight to a K-COT unit without any coking problems. So let's recap that feedstock flexibility and compare it to a conventional steam cracking. You'll see that ethane and propane, C2 and C3, cannot be fed to a K-COT. When we do a grassroots K-COT unit and we produce some ethane and propane, which is low value, we typically include a score along with the K-COT unit to handle the small ethane and propane recycle flow. Butane and straight run naphthas can be fed both to a K-COT unit as well as to conventional crackers. And then there are a slate of feedstocks that can only be fed to a K-COT and would be unsuitable for conventional steam cracking. Let's look at some yields and how they compare to conventional steam cracking. Here on the left, I made that comparison. You see that ethylene yields are similar between, and this is a paraffinic naphtha that we are looking at here, a little bit less than 30% of ethylene. Propylene, however, we produce significantly more in a K-COT unit. And you'll see that in a typical steam cracker, you can run at P to E, propylene to ethylene ratio of approximately 0.5. But in a K-COT on a paraffinic feed, we will reach 1:1 on a propylene to ethylene ratio. When we look at olefinic feeds, this becomes even more prominent. For example, on a C4 raffinate, you see we produce significantly more propylene than ethylene. And we can reach P/E ratios up to 2. There's no comparison here for olefinic feed between the K-COT and the conventional steam cracker. As I already mentioned, these feeds are very suitable for conventional crackers. Let's look at the flow scheme of a K-COT reactor. You see there are three streams that are fed to the converter: a feed stream, a fuel oil stream, and an air stream. And we'll follow all these through the process. Now let's start with the fresh feed. It is preheated in a feed effluent exchanger and then fed to the bottom of the reactor pipe. It is here mixed with hot and clean catalyst, travels in a fluidized bed arrangement to the top of the reactor, where it enters the disengager. In the disengager, cracked gas is separated from catalyst. The cracked gas then leaves the disengager from the top, goes to the feed effluent exchanger, and then to an oil wash tower, where fuel oil is mixed with the cracked gas. This has two purposes. It reduces the temperature of the reactor effluent, it quenches it, but it also washes out catalyst that remained after the cyclone disengager. So it's a secondary separation of catalyst from the cracked gas. Then the cracked gas, the reactor effluent recovery unit, which we'll be discussing at the next slide. Let's see what the catalyst do. So the catalyst starts at the bottom of this reactor, clean. It promotes the reaction in the reactor, is separated in the cyclones of the disengager, then drops into the regenerator. In the regenerator, air and fuel oil are brought in to burn off some coke of the catalyst, as well as heat the catalyst. And then the heated and clean catalyst goes back to the reactor. When comparing this with an FCC operation, the basic flow scheme is exactly the same. But since an FCC will have a much heavier feedstock beyond C10, a lot more coke will accumulate on the catalyst, and it's the coke that provides the heat of reaction. The heat of reaction, this reaction is a highly endothermic reaction, so heat needs to be brought in. In an FCC unit, that's largely provided by coke on the catalyst. Since we will have significantly less coke in a K-COT unit, we need to introduce a fuel oil, which we do here. And we also need to introduce some regen air to burn off this coke. Obviously, the internals of this regenerator are critical and are part of our proprietary design. Let's talk a little bit about the K-COT recovery section. There's no scheme shown here, and that's for the reason that the recovery sections are always customized. And so they'll heavily depend on the type of feedstock used, but also on which products need to be made and what the specific specifications are of those product streams. So it's similar to a conventional steam cracker, and also there we customize the design. There's still a few items that are specific and to a K-COT recovery section. Some oxygen will travel in the pores of the catalyst and can end up in cracked effluent, cracked gas effluent, and this needs to be removed. So we will have a removal bed for oxygen, which typically combined with an acetylene converter. We have the quench oil column design, the quench oil that we showed on the previous slide. That's a special design. And we also have simplified arrangements for C4, C5s, and C6 non-aromatics that are often recycled in a K-COT unit. Of course, we design recovery sections for energy efficiency and minimizing capex. Here on the right, you'll see a reactor effluent producing the ethylene and propylene, always a tail gas, and a BTX gasoline. But this can be customized. C4 or C5 olefins can also be produced instead of a BTX gasoline or an aromatic gasoline. People may produce just the BTX and recycle the C6 through C8 non-aromatics. So a lot of customization is possible in the recovery section. Let's talk about the types of industries that are looking for a K-COT. So the first one is liquid crackers. Liquid crackers produce a C4 and a C5 stream and a non-aromatic gasoline, which are in their environment usually very low value. And these can be recycled to a K-COT. So a liquid cracker could consider adding a small K-COT unit to take the C4s and C5s and non-aromatic gasoline and recycle that to a K-COT to produce significantly more propylene. In integrated refinery petrochemical complexes, there are abilities to add a K-COT and provide a lot of additional flexibility. You can look at upgrading more of your refining as well as petrochemical products with a K-COT unit. Thirdly, and this is something we've been doing recently on a few projects, refiners that are looking for vertical integration. Refiners with an FCC already produce propylene, but a K-COT unit to be added to their refinery can significantly increase their olefins productions. And lastly, the plants such as Fischer-Tropsch plants, CTL, coal to liquids, and MTO and MTP facilities that can look at converting some of their byproducts into lower olefins. Okay, this is a scheme of it's a very simplified scheme of a refinery with a crude and vacuum distillation unit. In this case, a reformer to produce gasoline and naphtha, a diesel HDS unit to produce a low sulfur diesel, an FCC unit producing propylene, butenes, naphtha, kerosene, and a cycle oil, as well as a fuel oil. And lastly, a delayed coker producing coke and coca like naphtha. This is your refinery configuration. You're producing several products here that can be upgraded with a K-COT. So a refiner can think of a vertical integration, add a K-COT unit, take some gasoline, mixed butenes, light naphtha from an FCC or a coker light naphtha, and turn those products in high value olefins and high value aromatic gasoline. We are working on several projects, in particular in China, where we are doing exactly as what I described in the previous two slides. And when we do this, we can look at a variety of ways to minimize investments. For example, we can review if it's necessary to debottleneck some units, a gas plant possibly, or BTX extraction unit, or other downstream units, instead of building all these new. We can look at the optimum product slate. We can limit the number of products, for example, only ethylene, propylene, and a high octane gasoline. Or we can look at other possibilities for product slates and minimize investments. Also, a standalone K-COT can be economic even for small naphtha feed quantities. And as I said, we're working on several of these types of projects in China. Let me get to the combined olefins process. This is what I refer to in the slide where I said ethane and propane cannot be led to a K-COT unit. So in this particular case, there was an end user, a producer of olefins through a thermal cracking process with a large slate of fresh feeds, which can feed these pyrolysis furnaces and produce a cracked gas that goes to a recovery section. We discussed and then implemented a addition of a K-COT unit to take some of these feedstocks, or actually additional feedstocks that the cracker previously did not process, bring it to the K-COT, and the cracked gases from the conventional cracker and the K-COT both are led to a recovery section. Recycles, the ethane and propane in particular, go back to the cracking furnaces, and in particular olefinic streams, C4, C5s, would be recycled to a K-COT unit. And with such a setup, an end user is ultimately very flexible in what they produce and what they produce at which time. Everybody in our industry faces a continuous change of product prices and likes to adjust their operation to maximize their returns. This slide shows prices of ethylene, propylene, butadiene, and benzene in Asia in monthly intervals. And you see that some of these prices, in particular butadiene, is varying very significantly. So what we did is we looked at that cracker K-COT combination that I showed in the previous slide, and looked at the options that this petrochemical producer has in feeding fresh feed either to the cracker or to the K-COT unit, and recycling C4 plus streams either to the K-COT or to the conventional cracker, knowing that they produce a different yield. And we found that for every month there was a positive gain. So there was a benefit of the flexibility to by the addition of the K-COT unit, varying from $10 per ton of ethylene to well over $100 per ton of ethylene. And the average increment was $58 per ton of ethylene produced, which is very significant in this industry, and it had a simple payout in less than 3 years. Let's talk a little bit about our references and K-COT experiences. We have 3 units in operation. 2 are standalone units with full product recovery, and 1 is integrated with a existing steam cracker. They're all operating well. And we have 3 units in EPC phase, and these are all units where refiners are looking to vertically integrate and produce petrochemicals. 2 of which will produce a dilute ethylene for an EBSM unit. They all produce also a polymer grade propylene. And we have a demonstration unit that we used about 10 years ago to collect yield data on a very large variety of feedstocks. And I mentioned some of these advantages. I want to just come back to them. So K-COT produces higher propylene yields and also lots of aromatic gasoline. It has a very large flexibility in feedstocks. We can do very large reactors. So we've done plants up to 1200 kTA of ethylene plus propylene with a single reactor. Feel very comfortable doing that. but it can also be applied in small capacity. And it's all based on well-proven technologies, catalyst performance, orthoflow, which we've used in FCC for so many years, and back-end separation in olefins plants, which we've also been designing since the 1950s. Of course, I would have preferred to give this presentation to you in person instead of doing it online here. I'm providing here my contact information, as well as my colleague Dario Guzman, who's in Argentina. Please reach out to us if you have any questions. We'll be glad to have discussions with you, and look forward to that. Thank you very much for your attention. Well, thank you very much for listening on this presentation. You see, I did this presentation from my home, and I would have much rather done it in person at your office in your plant. You've seen my contact information at the last slide. If you need any further details, would like to discuss it, please give me a call or send me an email. Thank you very much.
APLA organiza la primera reunión virtual latinoamericana de petroquímica, que tendrá como objetivo generar un espacio de nuevas experiencias y oportunidades, desafiando las nuevas tecnologías y adaptándonos a los nuevos paradigmas de negocios. Sigamos conectados. APLA Anual Virtual, 9 y 10 de noviembre. Los esperamos.